Hi, welcome to the March talk for Rust Dublin meetup. This is our first talk of 2024, a bit of a slow start to the year, but hopefully we have another talk lined up for next year. For the moment, we're going to stay remote. We did a few on-site last year, but the numbers were low. But we definitely want to have a few more this year on-site. So if anybody's got any interest, just let us know in the chat, etc., etc. To get into the topic, today's talk is about kind of parsing data, for want of a better phrase. I think we've all come across JSON, XML, and well-structured data, and there's lots of libraries out there for us to be able to parse that. However, at times you're going to encounter custom data types or data that's not well structured, and one approach, I suppose, is to use a regex for things like this. And we've all encountered regex hell towards the end of a lot of code. So another approach to that is to use parsers or combinators, and that's what the talk today is about. And I'm going to let our speakers talk about that. So just to quickly introduce Luciano, I think we all know he's kind of been a great a speaker for us over the years. And today he's accompanied Roberto, who has worked a lot with Luciano on the advent of code. And there is a lot of other content from Luciano and Roberto available if you want to look that up afterwards. Really good talks on their personal channels and blogs. This video will be available on our channel in a couple of days. Brian's going to do all the editing, etc., etc. But for now, we're going to kick off. If you have any questions, just pop them into the chat as they pop up, and we're going to take all the questions towards the end, but we'll leave plenty of time for that. So I'm going to hand over to Luciano and Roberto, and thanks very much.
Awesome. Thank you, Alan, for the intro. I'll share my screen, and hopefully you can see that. And Roberto, whenever you're ready, I'll leave it to you to start.
Yeah, tell me when the screen is shared.
I think it is now. Yeah.
Okay, so hello, I'm Roberto. I'm lazy by nature, Pythonic by choice, old enough to be rusted, and I principal engineer here and there. And we can connect on link3/Gambuzzi, my surname. Then I leave it to you, Luciano.
All right. Hello, everyone. I'm Luciano. By the way, before I tell you more about myself, all the slides are already available online, and you can get the QR code there or the link. We will also share the link at the end, but it's because we have a few code snippets that maybe you want to check out later, so it might be handy just to get the slides. Okay, again, my name is Luciano. I have a few badges that are totally not relevant for this talk, so I'm going to skip them. I work as a senior architect at Fortiorem. It's a cloud consulting company. We do lots of AWS. So if that's your thing, definitely feel free to check us out and reach out to me. And also totally not relevant, but something I have to say every single time, I am the co-author of this book about Node.js and design patterns. So if that's also your thing, please check it out and let me know what you think. And you can find all my contact details there. I'm generally available on Twitter, LinkedIn, Mastodon, Blue Sky, and whatnot. So whichever is your channel of choice, you can reach out to me, and I'm more than happy to have a chat. So let's start the talk. What the heck is a parser? And one, I guess, not necessarily academic definition is a parser is a program that can turn text or bytes into structured information. And to really understand what that means, we can take this example. So we can imagine we have a string that is describing some kind of point in a 3D space. So this can be a potential way to represent that information as a string. But as it happens, we might need to use that information in a program. So we might want to parse that information and extrapolate some elements and maybe copy over this element into a struct that might look like this. Because, of course, this kind of struct is something more useful because we can access the individual items in the struct and do something more useful with it. So how can we actually parse a string like that and build such a struct? Now, there is a very naive approach that I'm sure everyone has used at least once in their lifetime, probably more than once. And I like to call it string split like a madman, because you start to split stuff and discard stuff, and eventually you come up with some information that you can use. And if we want to use some pseudocode, it might look like something like this. So this is a variable that contains our input. Then we might use some kind of information called, some kind of function called split that says, okay, take this string and split in two parts, looking for a delimiter that is effectively a column and a space. And then the two parts, we're going to call them on one side label and on the other side remainder. So we are basically separating the string in two parts, removing that separator in the middle, and we have a label on the left side and a remainder on the right side. Now we can keep going and say, okay, we don't really care about the label, so let's look at the remainder. And we split again, this time looking at a parenthesis, open parenthesis. And what we are doing, we are just trying to get rid of that parenthesis. And you can imagine we can keep going. We split again and remove the closing parenthesis. And then we split again. This time we can split 3 times. So we want to get 3 segments. And we just split based on comma and a space. And at this point, we have X, Y, and Z, which is the information that we really care about. Now, this is an approach that works. You can use it, and it's mostly fine, I guess, for the most part. But there are a few problems. It's not always suitable because you might need to have very good delimiters, and not always you have delimiters that you can rely on. In this particular case, we have, for instance, parentheses and quotes, and we have parentheses and commas and columns. So that's a good use case for that. But in other cases, you might not have such delimiters. So it can be very simple for simple stuff, but it might get increasingly hard for more realistic use cases. And the other thing is that it's not something where you can easily handle errors. Like, you need to write a lot of code to be able to handle errors consistently. And probably that's not something you want to do, especially if you have a complex protocol that you need to parse. It might get very out of hand very quickly.
Instead, you can think of use a regex. We have regex, and we take the same input, so the same string as before. Then we say, okay, what should I match with a regex to be able to extract those 3 numbers that are there, because I just care about them. I will say that we have a string that starts, and then it starts with the label point, colon, space. Then I want to match an open round bracket. I have to escape it with the backslash because the round bracket is a special character for the regex. I have a capture group. The capture group says there could be a minus sign. Then there will be a number of numbers, at least 1 or more numbers. And that is our definition of numbers. So we also match the comma, and we match another capture group, that is the second number of our point. Then we have a third capture group, that is the third number of our point. And then we match the closed round bracket and the dollar. As you can see, this is a little bit complicated to read and complicated to write. And we define, like I said before, the capture groups. So we will have 3 capture groups, 1 for each number that we want to capture. They map to the relevant number, and we can name them. We can, through every regex library that is out there, you can name a group. So you will give an alias to this group that is indexed by number. We have X, Y, and Z, because those are the 3 coordinates of our 3D point. Yes, those underlined. Yeah, X, Y, and Z. But there is a problem. There is something to be aware of. Rust doesn't have in the core libraries a regex library, so we have to add this regex library to be able to use regex in Rust. To do so, we need to use the cargo add regex command. And yes, sadly, it's not something that comes out of the box. We have to install it. Not a big deal. It's easy, but something that you have to remember to do. So let's look a little bit at some Rust code for real, not pseudocode this time, on how to parse our 3D point in a 3D point structure. First of all, we have to import our crate that we installed before. We have to define the struct of our 3D point. It will be 3E32, X, Y, and Z. Nothing complicated. Then we start our main function, defining the regex itself. The unwrap here is safe, because unwrap in this case fails only if we define a regex that is not correct. But in our case, this regex is correct because it's hard-coded and because we wrote it and we tested it. Notice that there is an R in front of the open double quote because this is a raw string to avoid to have to double escape the backslashes, because the backslashes are not escaped in this string because they are used to escape the special charter for the regex itself. Then we capture on top of a string with our regex that we just compiled, let's say. This unwrap is a little bit less safe because if the string is not matching, that will throw a fatal, that will error out. Because in this case it's not, because the string is hard-coded, then it's valid, so it will go on. But remember, when you capture on top of a regex, some input that can be an input from a file, an input from the user, always check if there is an error and always handle the error. Here, for the sake of simplicity, we skip that. So the output of this will be a captures data type that will contain the full match, the key 0, the first one, that doesn't have an alias. Then it will contain another 3 groups, 1, 2, and 3, that will be our numbers, 22, 17, and -11. And they will also have an alias, X, Y, and Z, that is then used to address them. So when you have this capture group, you can address them by number or by alias. In our case, here in this line 14, where we create the point3D instance of this data structure, we refer to the capture group by alias. We parse it as an integer and we unwrap. Here, the unwrap is safe because of our capture group that only capture numbers. So it captures something that is always a valid number. Otherwise, it's failing before arriving here. So it's safe to unwrap in this place. We unwrap X, we unwrap Y, and we unwrap Z. We have our point, and then we print it out. So what are the problems with this approach? Some people, when confronted with a problem, think, I know, I will use a regex, and now they have 2 problems. This is a famous say that is going around. So yes, regex have their perks, but they also have their problems. Point 1, they are hard to debug. They match everything or they match nothing. They don't tell you why they didn't match. They just don't match. So when you start having a strange behavior in your software, you have to think, oh, could it be that the regex was not matching some kind of strange input that I was not expecting? And instead of giving you an error, you have to try and debug. Then also learning to write regex is complicated, require a lot of practice, and the final result is not the most readable stuff on earth. And they have limitation. For example, they are not very well suited for parsing nested structures. There are languages like C# where they have their own kind of regex that can match nested structures, but by the book, regex for a regex is hard to match the closing curly bracket of an open curly bracket if there are more nested curly brackets in a string, for example, a JSON. So it's hard to parse a nested JSON with regex. More than hard is impossible. So what is the next natural step after this?
So the next natural step is what we can call consuming parser, sometimes also called parser combinators. And the idea is that you want to have a mechanism that allows you to consume a little bit of information and match that the information is actually what you expect, and probably try to convert that little bit of information into something useful. And again, let's see an example because it makes it a little bit easier to understand the concept, and it's always the same example, and we'll start with some pseudocode. So let's imagine that we have a function that just says, okay, you have an input. I just want you to read, meaning consume the first part of the string, and we expect that part to be a label. So we don't really know the code of this function at this point, but just imagine that somehow we implemented this piece of functionality that knows how to consume the initial part of the string until it looks like a label. And the next step, so once we do that, we are effectively splitting the string in half, if you want. The first part is the parsed data, so the data that we already consumed, and the rest is the remainder string. So we still need to process the rest of the data. Now we have another function, let's just call it read separator, that just looks for, it only consumes the remainder data. So we kind of discarded already the first part. And it looks for a separator, in this case, a column. And effectively, again, we have other two parts as a result. The first part is what we just matched, so what we consumed and matched, so the column itself. And the yellow part is the remainder. And we can keep going on. The next one is going to look for a space. Same idea. We match the space. We have a remainder. The next one, maybe it's a little bit more sophisticated. We can say, read a tuple of integers. So you can already see that you can make these smaller parsers as simple or as complex as you want. And it's on you to effectively define how to make them easily composable and reusable. But let's just say that we have this information, this function that allows us to process an information that looks like a tuple of integers. What it's going to do is just going to take all the information. So it's going to look for parentheses, for numbers, for separators, and it's just going to give us 3 numbers already looking as an integer. And at this point, the remainder is the empty string. Now, this is the idea of consuming parsers. And one of the obvious advantages is that once you start using this approach, handling errors becomes so much easier, because as soon as you fail, for instance, imagine that now the input is hello world, and you try to read a number from hello world, it's not going to match immediately, and it can stop right there. And it's just going to tell you, well, I couldn't match a number on the remainder string, which is hello world. So when you see an error like this, it's just much easier to relate what was the input, what was the specific part of the matching that you were trying to do, and why did it fail, which is not something that you get with regex. You might get it with string splitting, but it's on you to write all the error code and the error reporting. Now, one library that allows you to implement this idea is nom. We will talk at the end of the talk about some alternatives, but it's kind of a default, as far as I know, in the Rust ecosystem, has been at least for the last couple of years. And again, it's not something that you get by default in Rust, so we need to install it using cargo. And with nom, it's going to look more or less like I described before. So here we have a little bit of realistic Rust code. Again, the input is always the same. And we can assume that we have created a function called parsePoint. What we are going to do, we're just going to say parsePoint using the current input. Of course, this operation can fail. If it doesn't match, it's just going to give us a result that looks like an error. Here, we know it's going to be fine, so we can easily unwrap. And then it's going to return us a tuple with 2 items. The first item that we are just ignoring with the underscore is the actual remainder string. So we don't really care, because we know that parsePoint is going to parse the entire string. And the rest, the second element in the tuple is the actual point as a structure information. Now, this is, of course, a little bit vague, because to really understand this, we need to look into the parsePoint function. So the parsePoint function could look like this. And this is actually one of the distinctive features of nom, that all the parsers that you write have more or less this kind of signature. So the first thing that you have is one argument, and this argument is generally called the input. So what is it that you want to parse? And of course, in this case, we are parsing a string, but nom is not necessarily limited to strings. You can also parse bytes. You could even parse your own sequence of tokens if you wanted to implement something a little bit more high level, for instance. Generally speaking, strings is the most common that I've seen, but again, nom is very flexible on that. The other thing is that the result here is an alias that noms provides you, which is effectively abstracting the error type. There is a specific nom error type. And then there are 2 generics, and these generics are, again, the input type. So what is going to be the remainder after you parse? And then what is going to be the data type that you are trying to parse with this specific parser function. In our case, we assume we have defined this pointed3D struct. So this is going to be the output that we expect if we are able to parse the string correctly. So somewhere down there, we are going to have all the parsing logic. And then at the end, right now line 4, we are going to have to return, again, this kind of weird structure. It might look a little bit weird, but in NOM, you are always thinking in terms of tuple, where the first element is always the input or the reminder, if you want, and the second element is the value that you actually parsed right now. Okay, so what is the first step? The first step is that we want to, for instance, match on point. And I have, again, the example at the bottom right of the slide. So this is the string we are trying to parse, just as an example. So the first thing that we want to make sure is that the string starts with point, column, and space. And NOM gives us a parser combinator. This is the way that they call the built-in functions that you can easily compose. That is called tag. And what tag does is effectively an exact match. So it's just going to succeed if the remainder string starts with that particular string that you are putting in the tag. The other thing that is interesting to note here is that there is a very functional approach. So this looks like currying, for instance, if you come from Haskell or other functional languages. So it's the idea that tag itself is a function which can produce another function. So it's a function where you can pass an argument, in this case, the exact string that you want to match, and it returns another function, which is the actual parser that can match exactly that string. And to use that parser, we have to call the function with an input. So we could have split this operation into two separate lines. So we could have said tag point and named that, I don't know, prefix parser or something like that. But it's generally more common when you see NOM examples to see this kind of use case where people are just saying, I'm going to create the tag parser in line, and then I'm going to call immediately the specific input that I want to parse. And this is just because generally this kind of parsers are one shot. You are not probably going to reuse the tag point somewhere else in the same function block. So this is effectively what we want to match. And this is the value that we want to match against. Finally, of course, every parser can fail, because what if the string doesn't start with point? Maybe it starts with a number, maybe it starts with something else. This is not going to match, and the parser is going to stop right there with an error. So here we can use the question mark operator just to effectively escalate that error and return an error type. Now, in this particular case, remember that we always get the remainders, which now we are calling input again. So we are kind of shadowing the original input. As we consume all the string we got as an input, we keep calling the remainder as input just for simplicity. The other element that we get is what we just matched. And we will be matching a string, or a string slice in this case, that only contains point, column, space. And we don't really care about that value. We just want to make sure it matches exactly that, but it's not information that we need to retain. So that's why here it's kind of safe to just disregard it with an underscore. Okay, then the next step, we can do the same thing to just match on a parenthesis. Then the next step is a little bit more interesting, because this time we know we parse point, column, space, open parenthesis. There will be a number there, or at least we expect it to be a number there. And we expect the number to be a sequence of digits if you look at it as text, but we should be able to convert that sequence of digits into a valid I32 type, Rust type. So this is another NOM combinator that you have it built in as part of the library, and you can use it every time you need to parse a number. It's just going to make your life easier because it gives you already a number type. And if it fails to parse the sequence of digit, or if it fails to convert that sequence of digit into a valid I32, you're going to get an error, and that error is going to be escalated. So now we have everything else that we need to complete this function. So we need to match a comma and a space, another number, a comma and a space, another number, and a closing parenthesis. And at this point, we were able to extract X, Y, and Z as I32s, and it's very easy to build our instance of that particular struct. Now, with NOM, you generally see people breaking down the problem into smaller and more usable parsers. We had a little bit of duplication in our code, so there is ways to refactor that in a way that there is less duplication, basically. And we can make things a little bit more reusable as well. For instance, one thing is that we might have a separator. Maybe we are building a larger parser that parses not just points, but maybe also triangles, rectangles, other shapes. other information, metadata. So maybe you might have this concept of separator in different places in the parsing logic that you're writing. So it might be useful to just write a smaller parser that can only match separators. And actually, we can make the idea of a separator a little bit more flexible. Before, we were just saying it's always a comma separated by one space. Maybe we can extend the idea and say, well, there needs to be a comma, but I can have 0 spaces or n spaces. It doesn't matter. We can make our parsing a little bit more lenient that way. So here we are introducing a new combinator to do that again provided by NOM, and this is called pair. And what it does, it basically allows us to combine 2 different parser, and it's going to try to apply them in sequence. So it's going to apply the first one and then the second one, and it's going to, if everything succeeds, if everything matches, it's going to give us back a tuple that contains the result of the first one, followed by the result of the second one. Now, another example that we might have is parse coordinates. Maybe this idea of having a sequence of 3 integers, it's something that, again, we might want to make it reusable. So we can also build a parser for that specific part of the information. So we are only trying to match, for instance, 22, 17, minus 11. And we can use another combinator. This time it's called tuple, and it's kind of a generalized version of the pair one, where pair only allows you to concatenate 2 parsers. Here you can concatenate as many parsers as you want. You just provide all the parsers in a tuple. So in our case, our sequence of parsers is going to be I32 separator, I32 separator, and I32 again. And notice that we are reusing that separator that we just defined ourselves in the previous slide. So this is the idea that as you start creating your own little parsers, you can easily combine them together. And finally, once we have those 2 parsers, we can create the version 2 of our parse point. And the first part is always the same. We just want to match on an explicit tag that is point, column, and space. Honestly, I was a little bit lazy here. We could have said spaces, but you get the idea. And then here, what we are doing, we are combining other parsers using another combinator here called delimited, which what it does is basically allowing you to say, I want to parse some information, but I know that that information needs to have delimiters. For instance, an open parenthesis at the beginning and a closing parenthesis at the end. I don't really care about the result of those 2 delimiters. They just need to be there. So just give me back what is being parsed in the middle. So we are just using parse coordinates to really extrapolate information from our parser. And at that point, this is maybe a little bit more advanced version of the parse point, but we are making it a little bit more reusable, and we have less duplication of code. Now, at this point, we learned, just as a summary, some useful NOM combinators. And I think NOM takes a little bit of practice just to get used to the different combinators that you have available. So it's probably a good idea to do a recap. The first one we saw is called tag and allows you to do an exact string match. Then we have I32, which allows you to check if whatever is in the remainder of the string looks like a number. And as long as it looks like a number, it's going to be consumed. And when everything is going to be consumed, is going to try to parse that sequence of digits into an actual I32. And if it succeeds, you actually get out a value that is a number and it's not just a string slice anymore. Then we have space 0, which can match 0 or more spaces in a sequence. Then we have pair, so you can take 2 parsers and apply them in sequence, and you get back a tuple with 2 values, which are effectively the result of the 2 parsers individually. Then we have tuple. It's kind of a general version of the previous one where you can effectively concatenate n different parsers in sequence. And then we have delimited, where you basically say parser number 1 is the initial delimiter. Parser number 2 is what we really want to process as useful information. Parser number 3 is the closing delimiter. There is a very good NOM combinators cheat sheet on the repository. When you get the slide, you'll be able to click there. And the idea is that you have a list of all the most common combinators, and that list also tells you they are grouped in kind of logical groups, and it tells you more or less when do you need to use that particular combinator.
So let's look at the RESP protocol itself. RESP protocol is the Redis Serialization Protocol, and what is it exactly? Is a binary protocol that is defined as a binary protocol, even if it's very human readable, that is used to control as control code ASCII standard characters to define sequence of informations. This sequence of information always end with a CRLLF, a carriage return, and a line feed, and is also used internally to separate the different parts of our data types. The first byte of every payload is identifying what will follow. So there are different kind of types. In this RESP protocol, there are simple, bulk, aggregate, so simple strings, bulk strings, arrays, maps, sets, all kind of stuff. So this first character is telling us which one is the following type. And here we have a table that shows us what are those types. We have the plus, that is a simple string, the minus is a simple error, the integer is a colon, the dollar is a bulk string, array, nulls, booleans, double, big numbers, big errors, verbatim strings, maps, set, and pushes. We will explain some of them later on. So let's look at an example message. Let's start with something simple. We start with plus OK. That is a simple string with OK written in it. And you can see that it starts with the plus, then there is the string, and it terminates with /r/n. So then we have another simple example that is the simple error that starts with a dash. Then there is something written in it. Because of the protocol, normally there is some kind of code at the beginning and then a free text string. This is not implemented in the protocol itself. This is just a convention. And then again, it ends with /r/n. And this is a simple error. Then colon from the table before, if you remember, is the integer. And we have the integer, but we have the integer as a sequence of ASCII characters. So we have 1000 here, we have colon 1000, but this will be 4 bytes, 1, 0, 0, 0 in ASCII. So it will not be a binary encoded 1000 bit by bit. And this is an integer. Again, we can go with the more complicated data structure. For example, if we want to have a multi-line string or we want to have a bigger string, we have a bulk string. A bulk string starts with a dollar, then there is a number, a separator /r/n, and the string itself. That 5 is the length of the string that will follow. So this tells us how many bytes we need to parse going on, 5 in this example, to get the full string. In this way, it's possible to add carriage return inside the string that otherwise will break our protocol. But knowing the length of what we have to read, there is no need of doing anything special there. Then we can go with aggregate types, more complicated one. This one is an array. You can see there is a star, two, that two is the number of element of the array, /r/n. Then $5, so the first element of this array is a bulk string of length 5 that contains hello. Then there is another element of length 5 containing word. And this is an array with 2 elements. And then going on, we can have doubles, again represented as with ASCII characters and not with binary characters. We can have big integers or big numbers. We can have maps, where we have, for example, here we have a map with 2 elements. Then we have the key that is first, that is a simple string. The first value is an integer with value 1. Then we have a second key that is called second, again as a simple string, and it has an integer value of 2. But we wrote a parser for this with nom. What we did, we started defining the data structure itself. So we defined an enumeration of all these possible data types. All these possible data types contains sometimes a string, a slice of a string, to be honest, an integer 64 for the integers. The null contains nothing. The null is just a null. The boolean itself contains if it's true or false. Double, we kept the string because we don't want to use decimal, so enforce an external library, and we don't want to use float to avoid to lose precision. Same for big numbers. We keep an str because we don't want to force a library for big numbers handling, because there is not a library in the core of Rust for this. You have to install a crate. But it's important to notice that, for example, for array, we have a vector of value. So we have a vector of ourself. And there are a bunch of types that have this. There is the array, there is the map, there is the set, there are the pushes. Pushes are basically arrays that come from the server to the client. So these types this type is basically a recursive type because it can contain references to other instances of itself. This made some stuff a little bit more complicated. For example, if you see the set is not a Nash set, but is a B3 set, because to be a Nash set, you should be hashable, obviously. But because you can have mutable values in value, those are not hashable. How do you hash an hash map? How do you hash an array that can change? So for this reason, we use even for the map, we don't have an hash map, but we have a vector of keys and vector of values and so on. So we tried to stay in types that were not enforcing any kind of implementation to the user of this library. We first wrote a first parser for parsing a value of this. And here we use a combinator called one-off. One-off say, take from the input one of these characters. And we provided all the list of the possible characters that the RESP protocol is supporting. Then we said, okay, let's make a match based on this type, on this character. And based on the character that tell us what kind of type is following, we select the right parser for our input. So we selected the right parser for that type of value. We use it and we return it directly because it has the same signature result str value, because we always return a value from everything. So, and this is the first idea that we had to parse the RESP protocol. But then we went for an alternative approach. The alternative approach is to use the alt combinator from NOM. What is the alt combinator doing? The alt combinator is taking a tuple of parsers and is trying all of them until it finds the first that is not failing. So because of the RESP protocol, this is quite fast, because if a parser fails, it fails at the first character, because it will find plus, okay, it's not starting with plus, I fail. And then alt will take the second one. Starts with a minus, yes, no, and it goes on like this. And our function, our parse value, now is simpler because it's just alt of this list of parsers of the input. Done. No intermediate variables of any kind. Yes, we are here. But to do so, To do so, we had to define some delimiter and some functions to help us, like we did before. So we created the CRLF combinator that is basically just a tag that match /r/n. This will fail if the input doesn't start with that. And then here there is an example of one of these parsers, the parse simple string. So this is our CRLF. And then we have the parse simple string. Parse simple string, again, is taking a slice str as an input, is giving back our result. First of all, is checking that the input starts with a plus. If we are facing not a simple string, this will immediately fail, and alt will go to the next parser. let's say that, for example, our simple string example down there at the bottom of the slide, we match. So we go on. Now we use another nom combinator called terminated, let's say, and also take while, let's say, take from this string while the character is not a slash r and a slash n, so while the string is something else, take that until you are terminated by a CRLF. So it will consume the string in this value, that and value will be as in this case will be a slice of str, yes, of this input. There is the question mark, so if there is something wrong or there is no terminator, this will error out. And when we have our slice in our value variable, we return the remainder of the input and a simple string enumeration type with value inside it. And this is how we parsed a simple string. Another example can be to parse a bulk string, like we said before. There is you can see the example below. There is a $, a number, /r/n, and then there is 19 characters, then another \r/n. How we did this? Again, the signature is always the same. The input say that the tag say that the first character of the input should be a $. We then parse a U32 terminated by CRLF. U32 is not the Rust U32, it's the nom U32 combinator. So we parse a U32 number, length will be a number. At that point, we use again the terminated by CRLF. Take takes a number of characters that you provide. And we provide length, casting that as usize, because we parsed the U32, but take wants a usize. So now this is taking 19 characters terminated by CRLF. And if one of these instructions fails, this parser is not the right one to use. If we arrive to this line, it means that this was the right parser to use, and we return our bulk string enumeration with the value that we just extracted. Again, we have the array. Let's go a little bit faster on this because same signature, we match a star. We want to know how many elements we have in the array. Here we use another nom combinator that is called count. And count applies another parser. It's not like take that takes a number of characters. Count takes a number of parsers value. So here there is basically a recursive call to our parse value function and say, I want to call this parser length times an array of 2 elements here. So we will call parse value 2 times and we will get 2 values out of it. Values will be already a vector, so a vector of values. So will be already the right type to use inside our return value for the enumeration array. Then obviously we wrote parser for all of these types, but we are not going to show you all of them.
Yeah, otherwise we will kill you by boredom. Anyway,
yeah,
I think it's good now to do a good recap of the other combinators that we learned so far. So one off, you can match one char or one car, I guess I should say, from a list of allowed ones. Terminated, basically what it does allows you to apply one parser, and then it's going to look that the remainder string starts with the content of a second parser. So we use this to make sure that once we parse something successfully, that is actually followed by a terminator, in our case, /or/n. Then we have EOF, so end of file, we can say, is an interesting one because it basically doesn't really match anything. It actually checks that the remainder string has length 0. So you can really use this end of file only with input types that implement length, so that are implemented trait size. Then we have alt, the one we used at the very beginning of this protocol, where we try to effectively say, try to match a sequence of parsers and stop as soon as the first one matches the string. Then we have take while, so it's going to allow you to keep consuming cars and basically stop only when a specific condition applies. And then we have take, which basically says take a certain number of characters. Finally, we have count, which is useful when you know you need to repeat a parser a certain number of times. So you can just say count this parser n times, and it's going to give you back a vector of all the matched values, one for every repetition of that parser. Now, if you want to look a little bit more how we implemented all of this, again, we're not going to show you all the examples, but the library is already published. It's called TinyResp. We haven't used it for anything useful yet. We plan to do more coding challenges, maybe where we try to build our own Redis. And then at that point, maybe this library is going to be useful. But right now, it's just there for people to use it. So if you find it useful, let us know. If you want to contribute and make it better, of course, all of that is welcome. And we recorded in a series of live stream our exercises in trying to make all of this happen. So if you want to see the two of us screaming at the Rust compiler for like 3 hours and a half, which is probably not a great thing to do, but if you're crazy that way, you can check out the recording on YouTube. There is a playlist with all of that, and that's the link. Now, I have one last bit before we go into the conclusion, but I'll leave Roberto to describe this part here.
I will fly over this because we don't have a lot of time, but basically, can we use GNOME to parse binary formats? The answer is yes. We took a very simple binary file format, the STL file format. This is from the wiki page. This is what the wiki page described the format. So there is 80 bytes that are an header. There is a U32 of 4 bytes, 32, of number of triangles that will be described. Then there is this number of blocks of 50 bytes, and every block of 50 bytes is made of a normal vector made of free float, free vertices of the triangle in a three-dimensional space, and a uint attribute byte count that is something that I always found 0 in the STL. I checked, but some editor use it to store color of the triangle and other properties that are not not standardized. So it's just an integer. But and there is a monument in Dublin with this teapot in Smithfield, in the Smithfield Square, because this is called Utah Smithfield pot. How is called this one?
Yeah, I never understood, by the way, why this monument was in Dublin. It's literally the Blender example that the first 3D example that you see anywhere. And then I realized while I was researching it that the square where it is called Smithfield, and this teapot is called the Utah teapot. And apparently one of the biggest cities in Utah is called Smithfield. So somebody made this weird connection and they decided to put this monument in Dublin. So if you are in Dublin, it might just be a fun thing to know and see.
Yeah. But we did to parse this binary format. Again, we imported a bunch of stuff from GNOME, some consumer that we already saw, some combinator that we already saw before, but we imported the binary ones, LE_F32, LE_U16, and U32. LE stands for little endian, because when you parse a binary number, you need to know if the most significant and less significant byte is first or last in the file. And STL is working in little endian. Little endian is basically the encoding that also the Intel CPU are using. Motorola was using big endian. ARM can use both, but is mainly little endian. So we import the library. We define our structure that we will answer from this parser. So we have an STL file that will be a slice, an header that is a slice of U8. There will be a number of triangles that will be a U32. There will be a vector of triangles. Every triangle is made of free vertex, one vector for the normal of the triangle that tells where the triangle is looking at, basically, and our attribute, the 16-bit from before. Here is the parser that is parsing the binary block of 50 bytes that is the triangle itself. So it's taking as input not an str, but it's taking a slice of U8, an array of U8, is returning the same and a triangle structure. line 27, line 27, we basically create a free float parser that is a simpler version, is just a way of not writing tuple LE32, LE32, LE32 4 times, but we created this utility basically, and we use it to parse the normal, the vertex, and the attribute. In the end, we return through the OK, same as before, we return our leftovers and one triangle structure extracted from our tuple that we extracted with the DOM. After this, we have the parser of the main file that again takes this slice of U8 and returns this slice of U8 and an STL file. First line is take 80 bytes, because we don't care about what they are always 80 bytes. Then we parse with little endian U32 how many triangles we will have. So we have at most 4 billions and whatever triangles. Then with count, like we did before, we get that number of triangles that will already be a vector of triangles, and we just return it. The next step is to use this parser in the main function of our software, that is reading example STL from the disk, getting the slice of bytes, using the parser. Line 65, we discard the remainder. There should be no remainder, but STL, some editors leave metadata at the end of the file for extra informations. So we are not strict about this. We just discard whatever is after that. And we print what was inside the file. Inside the file, we will have an header with our 80 bytes. We will have a U32 with our number of triangles. This example was 2,466 triangles. And then we will have that number of triangles inside an array, inside a vector, with all their numbers. And attribute byte count, like I said, I always found 0 in these examples. But okay. I think we are a little bit over time, so I leave it to Luciano.
I'm going to quickly try to wrap things up. So if you need to do parsing, the first option is probably string splitting. It's a good option, but it gets messy really quick. So probably good for simple stuff, but don't overuse it. Regex is another valid approach, but there are pros and cons. They can be hard to learn, debug, and to get right. But sometimes they're just good enough to get the job if you have confidence in regexes. NOM and the idea of parsers combinators in general, it's probably a more interesting approach. It's a little bit more involved because, again, you need to learn that the way of thinking of parser combinators. In the case of NOM, you'll need to learn a little bit of the library and the helpers parser that you have built in. But once you are confident with them, it's definitely a good option to use. And you can build fairly sophisticated parsers that are still pretty easy to read. And also when you have an error, that generally the reporting of those errors is quite clear. So if you have an issue when you are in production or when you are testing, it is easier than things like regex to figure out exactly what's going wrong and what do you need to fix. And the other cool thing is that with NOM, with the same ideas and concept, you can also parse binary data, which is not always obvious when, for instance, you're using something like string splitting or regexes. Now, I have a little bit of a bonus content. You might be wondering why it is called NOM. And this is actually in the README of the repository. This is the logo, the official logo of NOM. And it's basically saying NOM will happily take all the bytes and basically eat them, right? Now, one thing that came to our attention in the last week, basically when we already prepared most of this talk, is that there are actually a couple of interesting alternative parser combinator crates in the Rust ecosystem that are emerging and getting a lot of traction. The first one is called Winnow, which is actually started as a fork of NOM, and it seems to be a lot more up-to-date than NOM is, and it's also trying to focus a lot more on the developer experience. So they are trying to kind of iron out some of the edge cases that are not super clear with NOM and try to give developers a better experience in terms of the API itself, some issue with error reporting, try to make that even better. So Winnow seems to be kind of a natural contender to NOM, but it's pretty much the same approach because it started as a fork of NOM. Then there is Chomsky, which I think has a slightly different API. So it favors more the idea of function chaining rather than a more functional style where you try to wrap functions one inside the other. So function composition. So you might like that or not, depending on which kind of programming style you prefer. I also had the luck to chat with Ed Page, who is the author of Winnow on Mastodon. And his take is that NOM is a little bit unmaintained at this stage because the last release was years ago at this point, and the new release was promised 1 year and a half ago, and it's not there yet. There is kind of a beta version that you can find with another name. I think it's called NOM 8. Like there is a crate called NOM 8, which is not the official one, but it's kind of a placeholder for people that want to experiment with the current work in progress. But apparently somewhere there was a quote of the author of NOM saying that it's not necessarily going to happen anytime soon, and it's not blocking anyone. So apparently Winnow now has a little bit more weight in terms of if you're looking for a crate that is going to be well maintained, probably it's a more obvious choice if you're starting a new project. And the repository also lists a bunch of famous projects that recently migrated from NOM to Winnow, just because there is a little bit of uncertainty around the NOM project. So everything we said, I think, is still very relevant, just because Winnow is going to be very, very similar to NOM. But just be aware that if you are starting a new project today, maybe it's better to look at the two and decide exactly which one you want to use going forward. Now, here we have a bunch of links with things we mentioned today, the NOM documentation, the combinator cheat sheet. There is another cheat sheet, which is very good if you want to understand how the error management works, and if you need to create custom errors, how you can do that. There are very good official examples in the repository, so definitely check those out. Our own library and the playlist with our live coding. And if you want to follow some of myself and Roberto, live streams, we do that on Twitch and YouTube, and there are links there. And that's all we have for today. So I think, I don't know how much time we have left, but I think we can be open for questions if you like.
Thanks, Luciano. Thanks, Roberto. Another great talk. Really well presented. I love your slides. They're excellent. We don't have many questions. I think it's because you're so good at explaining things. We had one from Tim early on. I'm not sure, Tim, if it's still relevant. It was... Sorry, I didn't note it here. You often expect a second generic to be an error type. Is there one general error type underlying the I result? Do you have a context for that?
Good question. I'm trying to find this question so I can highlight it. Was at the very beginning.
Is after Rust Dublin say the video is real.
Oh yeah, so it was at the very beginning.
Is below that one.
There you go. Okay. Yeah, so basically my understanding, and I think you're better off checking out the actual signature of that I result, but my understanding is just a type alias that effectively hides the error type and defaults that to a NOM specific error type. So you are kind of forced to use the NOM error type. And actually my feeling using NOM for a little bit is that they try to abstract as much as possible the error reporting. So you are better off just using the combinators, the basic combinators, and they will do the correct error reporting for you in case of an issue. Another thing that we wanted to show, but then probably there was too much stuff in our slide, is another combinator called verify that you can use when, for instance, you matched a string and then maybe you have a little bit of complex logic that you are not able to abstract with the default combinators or with another custom parser. Then with verify, you can just run arbitrary code. And if that arbitrary code returns an error type, then everything errors out with an error of type verify failed, something like that. So there are kind of escape hatches if you want to do a little bit of custom error typing. Otherwise, you might need to redefine this iResult type and be explicit about the result type. But I think at that point, you might have to map all the errors when you use the standard combinator. So it might get a little bit messy. But again, feel free to experiment. I think there might be room there for custom stuff. I don't know if Roberto, you want to add anything there.
No, you explained it very well.
Okay. You have another question there, Luigi, if you want to take a look at it and highlight it second from the bottom.
So is there an easy way to parse JSON with dynamic key value types? I think this is actually one of the examples that you have in the repository. So if I understand the question is, could you write a parser for JSON using something like NOM? And the answer is definitely yes. And I believe that one of the examples you find in the NOM repository is exactly to parse JSON. And I think there is even the JSON 5 extension, the one that supports comments. So it's even a little bit more involved than basic JSON. We can have the special guest, Roberto Scott.
Yeah,
wants some attention.
Yeah.
I'm not really seeing any more questions pop up here, Luciano, Roberto.
Yeah, in any case, our contacts are there online. So if you happen to review the slides at a later time and you come up with more questions, feel free to reach out and ask. I'm not going to promise we have all the answers, but we'll try our best.
Yeah, feel free to open pull request. Feel free to tell us that we don't write good Rust. It's true.
We are still beginners, so any suggestion is well accepted.
I saw a compliment flying through the text messages there halfway through it.
Yeah, here there is a comment saying that from Matt saying you would probably use Serdi for JSON. I probably agree with that. I think the JSON example is just more of an exercise if you want to understand how to parse recursive parsing, effectively recursive data structure like JSON or like the one we presented with the Redis protocol. So yeah, definitely use Serdi for everything that is JSON or JSON-like that is supported in Serdi. Lots of emojis.
My cat is telling us that there are no more questions. Yeah, are there other questions? It was a no.
Okay, I think we've answered all the questions that the audience has. Thanks a million again, Roberto and Luciano. Great presentation, as usual. And this video will be available on the channel in a couple of weeks, or probably sooner than that. But thanks everybody for coming along today. I think we can kick off a countdown to exit, Luciano.
Okay, thanks everyone for being here, and thanks Rust Dublin for hosting us. Have a good one.
Thank you. Bye.